Hello everyone, my name is Yang Zhang. I'm a PhD student from University of Connecticut. This is a joint poster with my teammate Ting Wang, who is also a PhD student. We both work with Professor John Tang at UConn. The title of my poster is Deep Learning-Based Joint Loosening Detection for Infrastructure Components. The goal of this research is to develop a data-driven technique for both structural damage and bolt loosening detection in infrastructural components such as the railway track and the bridge segment using the piezo transducer active interrogation. In the infrastructure components, they are heterogeneous for types, for example, the bolt joint loosening or the structural damages. Especially for the bolt joint loosening, it is difficult to build a model of fault condition based on the first principles. So in this research, we regard the damage detection of loosening bolt as pattern recognition or classification. So as shown in this diagram, there's two plates. They are fastened together by using 32 bolts that the piezo transducer attached to the top plate, and we're using the DSpace to realize the data acquisition. To classify which area has the damage, we divide these 32 bolts into 4 edges, these 2 short edges and these 2 long edges. And the data acquisition is simulated based on the Simulink model. And to facilitate the data acquisition, we use the chirp signals. It has two features. First, it has the variable frequency. It means the frequency can increase or decrease with time. In this, this can provide the clear and distinct information about the detected objects or anomalies. So this subplot shows the chirp signals, and this subplot is the responses from the structure or the plate structure. And when we get this data set, we need to do some data processing. So in this research, we're using a sliding window to slice the signals obtained into pieces. So the length of the sliding window is 35,000. So finally, we can have the 48 slices for each class, or we have the 48 data set for each class. And when we gather this data set, we need to train a deep learning model. As shown here, this is the architecture of a proposed deep learning model. Firstly, we convert the 1D sequential data into 2D sequential data, and then this data set will pass into several convolutional neural networks or polynomials, and also the flattened layer, dense layer, and finally, we will classify which area has the loosening bolts. So here are the results. As just mentioned, there are 4 edge locations of bolt loosening, 2 short edges and 2 long edges. So based on this confusion matrix, we can achieve 93% accuracies. It means, for example, if we identify the one bolt loosening in these long edges, so we will, using other post-filter techniques, will arrange the robots to inspect only on these long edges. This will reduce the maintenance costs. So to conclude the posters, we just say that the data-driven approach achieves the high detection accuracy for bolt loosening detections. And in future studies, we will consider more complex scenarios, especially the different severity levels of that bolt loosening. And then we're using the data-driven techniques to identify the severity levels of that loosening bolts. And we think the support by the Transportation Infrastructure Durability Center at the University of Maine under grants from the U.S. Department of Transportation's University Transportation Centers Program. And thank you.